This is chapter 14 part 3 and we are going to talk about the Diels-Alder reaction. In organic synthesis, carbon-carbon bond forming reactions are extremely important. Imagine how useful a reaction would be where you can form two carbon-carbon bonds in one single step, and that too without the use of any acids or bases or catalyst. So this type of reaction was actually developed by Diels and Kurt Alder in Germany in 1950, where their reaction involves the use of a diene reacting with a alkene to form a cyclic structure of this kind. Okay, so if you really look, we have formed two new bonds, two new carbon-carbon bonds. The reaction is classified as cycloaddition because of the formation of a cyclohexene ring. This part is called as the diene. There are two pi bonds here, and then this one is called as the dienophile, something that likes a diene. This reaction is also classified as a 4+2 addition, cycloaddition, because of the four atoms that are involved in this pi system and the two atoms that are involved in this pi system. The reaction all occurs in one single step without an intermediate, but in a mechanism in which the 6 atoms undergo bonding changes in the same transition state by way of cyclic reorganization of these pi electrons. So these type of reactions are called as concerted or one-step reactions. So we can draw the arrows in this way, where one arrow drawn this manner, the next one is here, and then the third one is here. Okay, this results in the formation of this product here. We can color these arrows, this over here and this, to show the new bonds that are formed. So here is the new bond and here is the new bond. Okay. The simplest of all Diels-Alder reactions is that of the 1,3-butadiene. Okay, so this is our 1,3-butadiene. So let's take another example here. Where we change the dienophile and keep the diene the same. So I have 1,3-butadiene again. Oops. Redraw this. 1,3-butadiene reacting with a dienophile which has a group attached to it, which is an aldehyde group. There are hydrogens here, which I need not draw. If you have a reaction like this, what would be the product? Again, a cyclic structure, a cyclohexene, now with the group attached to the carbon atom here. In general, the dienophile having electron withdrawing groups, such as, so we can abbreviate electron withdrawing groups as EWG, such as carbonyls, okay, which may include aldehydes or carboxylic acids. Okay, these increase the reactivity of the dienophile. Okay, so these increase the reactivity of a dienophile. So if you have another example where it's keeping the diene the same, okay, and let's change the group here to an ester, but now I have another ester group here. Oops. which is also a carbonyl. But now if you look, I have drawn it in a trans arrangement. Okay, so you have the two ester groups arranged trans to this double bond, and the product would again be a cyclohexene. Now with the substituents attached trans to the ring. Okay, so which tells us that the stereochemistry, it's a stereospecific reaction in that the stereochemistry of the starting material is maintained in your product. Okay, so we had a trans arrangement of the electron withdrawing groups in our dienophile, and that is maintained in our product. So the substituents like carbonyl groups, okay, like which contain carbonyl groups like this aldehyde or carboxylic acid, or there is another one, we can add that one too, which is a cyanide. Okay, what do? Is they are electron withdrawing groups, and they activate the dienophile more towards cycloaddition. Okay, so the electron attracting properties of these groups, they are electron withdrawing, right? So they withdraw the electron density from this, make this more electrophilic, as a result of which this diene, which is now the nucleophilic in nature, is going to react more faster with this dienophile, which has a electron withdrawing groups on it. Now regarding the diene, it's important that it should have a correct geometry in order to react with the dienophile. So let's discuss the geometry of the diene. For a Diels-Alder reaction, the diene should have a S-cis type of conformation. Okay, so let me explain what do you mean by that. So if you have a butadiene which has a trans type of conformer, this particular geometry is less reactive than when the diene is in a cis type of geometry. Okay, so this is called as the S-cis conformation, and this is the preferred geometry. Now in case of butadiene, since there is free rotation between the carbon-carbon single bond, this can actually rotate itself and change it into a cis conformation, right? And then react with the dienophile. However, there are cases where the trans geometry is locked, or there could be sterically hindered. It could be sterically hindered, and it won't be able to achieve this process. So in that case, the Diels-Alder reaction might be either very slow or it will not happen. So one example of that kind is something like this, where you have a diene again. Okay, however, you have sterically hindered groups attached to the carbon atoms. So if you have a compound like this, this would be much less reactive than when you have just a butadiene or with just one methyl group. So we have to be careful of what kind of diene we have to use in the Diels-Alder reaction in order for the reaction to go at a good rate. Also, this reaction is favored by a little bit of heat, but if excess heat is applied, the reaction actually can reverse, and that is called as a retro Diels-Alder reaction. Okay, so this reaction can be made to go back into the reactants by applying excessive heat, and that is called as a retro Diels-Alder reaction. So let's do a sample question here. There are two compounds that are given to you. One is this one, and the other is, so this is a dienophile, and then we have another dienophile, this one. Okay, so out of these two, which one will be more reactive? Remember that electron withdrawing groups like carbonyl groups or functional groups containing carbonyl group are electron withdrawing, and they make the dienophile more reactive. So this compound will be more reactive than this one. Okay. Another question, why is this diene extremely unreactive? Okay. So I have an example here where the diene has some substituents attached to it. The question is, why is this diene extremely unreactive? The reason is this has got bulky substituents attached to the carbon atom, right? So even if it makes a rotation through the carbon-carbon bond to get into the S-cis conformation, these bulky groups, the T-butyl groups, are going to be sterically hindered, and therefore this compound is pretty unreactive as a diene in a Diels-Alder reaction. Okay, so the two important things to remember regarding a Diels-Alder reaction is how to make the dienophile more reactive or more electrophilic. You can do that by attaching electron withdrawing groups, and the diene should have a S-cis type of geometry in order to do the Diels-Alder reaction. Let's take one more example of Diels-Alder reaction. So say for example I have this compound which is again a diene, and let's put a substituent to it, chlorine group, okay, and then react it with a dienophile which looks somewhat different now, a cyclic dienophile. Okay, so it's a benzoquinone, right? Let's take an example of this dienophile. Now look here, this dienophile should be more highly reactive because of the electron withdrawing group. Okay, so we have a diene which is a 2-chloro-1,3-butadiene. What will be the reaction? You have to also draw the arrows. Okay, so let's use another color here to draw the arrows. So it's kind of a little far, but we can. This is the arrow here, the next arrow here, and the next arrow here, right? So the three arrows which show the concerted mechanism. The product can be drawn where a cyclohexene ring is always formed. So you have the double bond here, and then now this part is a cyclic ring which also needs to be attached. Let me redraw this ring. So here we go, and the electron withdrawing groups are intact here. And what else? We have to put this bond here. Okay, this will be my Diels-Alder product. No, oh sorry, I forgot to put the chlorine. No, the chlorine should be back here on the carbon atom. Okay. So another way to make sure that you have drawn it correctly is by using numbers. So you can number the diene. So 1, 2, 3, 4. Okay, and then say for example to make this different, you can use a term A and B. Okay, for the alkene double bond. So so in that way you can keep track of all your carbon atoms. So this is my 1, 2, 3, 4, and these are my carbons which were labeled as A and B. Okay, and we used red color to show the arrow. These are our new bonds. This is a new sigma bond, and this is a new sigma bond formed between this carbon atom from my alkene and the carbon atom from my diene. Okay, so I hope these reactions are clear to you to understand the Diels-Alder reactions. Okay. Sometimes a question may be asked where the Diels-Alder product is given to you and you are asked to find out the dienes and the dienophile that form the product. So for example, if I give you the product as this one. Okay, so this is already your Diels-Alder product. You have cyanide group here and the cyanide group here. So this is my Diels-Alder product, and your question is, what are the dienes and the dienophiles that make up this Diels-Alder product? So you can actually draw the arrows to reverse arrows to undo this cyclohexane adduct. So you can start with the pi component of the double bond. Okay, so we can put this back here, right? This one back here, and then this back here. So that gives you the diene and the dienophile. So if you follow those arrows, you have a double bond here and a double bond here, right? And then your dienophile should be this. Now make sure you put the correct geometry. Both are have a cis geometry, so that means both should be pointing. Oh, you don't need the dark bond, just drawing it in this manner should be okay. So you can put Cn and then Cn here. So these are the starting materials for the formation of this product. So make sure that stereochemistry is taken care of, because Diels-Alder reactions are stereospecific reactions. Okay. All right. Now let's take an examples where we are using cyclic dienes. Okay, we used an example of cyclic dienophile. Let's do examples of cyclic dienes. So for example, one of the common examples that is used is cyclopentadiene. Okay, now cyclopentadiene is an extremely reactive diene because here the double bonds are locked in a cis conformation, right? So that makes the cyclopentadiene or 1,3-cyclopentadiene extremely reactive. Say if I have a cyclopentadiene, which I'm going to use as my diene here, and a dienophile, something that has got an electron withdrawing group. Let's take the ester again. Electron withdrawing group makes the dienophile more reactive. Keep it in the trans position. So we have the double bond O and then O CH3. So if you have a reaction like this, you can again draw the arrows, number the carbon atoms again. Okay, so if you wanted to number it, 1, 2, 3, 4, and then remember we said A and B for the diene, the dienophile. Arrows can be drawn where this goes over here, this goes over here, and this goes over to this carbon atom. So what will be your product? This is a little tricky to draw because now it's a cyclic diene, right? So your final structure will be a bicyclo compound where you have to flip this end, end of this carbon atom up, right? The way to draw this would be like this. Okay, you can call this as number 5 maybe, right? So your number 5 carbon atom is actually over here on the top. Let me draw it properly. This one. Okay, and then you have the new bonds that are formed. Let's make them as red color. So this is my new sigma bond that has been formed. Don't forget the double bond because that's how this bond comes here. And now what do we have left? We have these with electron withdrawing groups that need to be arranged, right? Now look, they were trans, right? So that means you have to draw one in this manner, pointing up, and the other pointing down. Okay, so these are the new bonds that were formed, the red bonds, and this is your structure. Okay. You have one group pointing up because they were trans and one group pointing down. Another example where we can take the similar type of example, but if you have both of them cis, okay, both the groups cis, say for example I have a cyclopentadiene again and I react it with a dienophile with both the groups cis to each other now. Okay, so again the ester group, and I have OCH3. What will be the product? What will the product look like? You will again have the bicyclo ring, right? Right. So if you go back and number this so that we don't, so we have 1, 2, 3, 4. Now the fifth carbon atom has gone up, and this is my A and B. Same thing here. We have 1, 2, 3, 4. Between 2 and 3, you have to make the double bond. And then here, since both the groups were cis to each other, you will have both pointing down. Okay, so you have C, O, CH3, and this one too will have a C, O, O, CH3. So here we have that carbon of our ester group. Okay, let's redraw this a little cleaner. C, O, O, CH3. Okay, let's make sure that it looks like they are both pointing down. Okay, so this is how you will complete the reactions using cyclic dienes. Now, it has been observed that whenever we have a possibility of forming a product where one of the groups can point up and the other group can point down, generally it is seen that the one that points down is more preferred, and we call this as the endo cycloadduct. Okay, so there are two cycloadducts that are possible, an endo product and an exo product. It's the arrangement of formation of this cycloadduct actually is preferred when the groups are endo to the ring. Okay, that means they are pointing face down to this bicyclic ring. So make sure that whenever a product is asked with then the and between an endo and an exo, choose the endo as your major product. Okay, so that's about reactions of Diels-Alder. Number of examples we discussed. Main thing you have to keep in mind how to make the dienophile more reactive and what kind of geometry a diene should be in order to form the product. And then the endo product is the one that is generally preferred because transition leading to the endo product is more stable, okay, or lower in energy. Okay, so that concludes this Diels-Alder reaction part. We will do more examples in the class. In the meantime, you can watch some more videos from other websites like the Organic Chemistry Tutor and also practice problems from your textbook.